Okay, so can everyone hear me? Yeah, good, we're good. All right, so my name's Tim Gross. That's my Twitter handle, which is why I will never be funded. So I work for Joyent. We're a subsidiary of Samsung. We operate a public cloud with global data centers. We've been using containers in production since 2006, which means that we're using a little bit different containers than you might be used to. Everything we do is open source. So you can take the same software that we use to run our public cloud and run it in your own data centers. Our customers include some of the world's largest retailers. We won't talk about who they are. Prior to landing at Joyent, I was running the operations team at a company called Drama Fever, a little media company, which is here, the technical team of which is here in Philadelphia. So stateful containers, right? So I'm going to talk about stateful containers today, and immediately we say, well, why would anybody want to run stateful applications in containers? But before we can answer that, we have to know, why are we running applications in containers in the first place? And there's really three reasons. I think they all kind of boil down to three reasons. Immutability, right? We can deploy a versioned artifact, right? We can answer this question, what version is our infrastructure? And those artifacts can be signed, they can be tested for function, for security. We have minimal overhead, right? We ship only the application, and you'll notice the asterisks there, because that's pretty much what this talk is about, and we'll kind of get into what that really means. And portability, right? So as close as possible, what we have in production is what we have in the developer laptop, right? This is really the problem that Docker solved. We have a development environment that is as close as possible to what you're running in production. We're abstracting away the infrastructure. But if you kind of, the container ecosystem, particularly as it came out in the first couple years of Docker, the Docker revolution, do we want to even call it that? Everybody said, well, you're only going to run containers for stateless applications, right? And I think a lot of this comes from this weird kind of, munging of the notion of containers and microservices, right? And then even then in microservices, people went and said, well, microservices means 12-factor applications. Which are all stateless, right? It's kind of, those are actually all different things, but because I think they all kind of hit the zeitgeist at the same time, this is what everybody was saying, don't run state in containers. The problem with that is, good news everyone, turns out that your stateless application probably has a lot of state with it, right? So a couple of reasons why. So TCP, we're probably all using TCP for applications, right? These are stateful. If your application stops, and the client sends a new packet to it, and that application comes back up in the meantime, it's going to send a reset back to that thing, and you will get a 500 error on the client, right? There is state being maintained, and that sounds like a very trivial amount of state, which it is. But there is definitely some state there. We also have service dependencies, right? So like when I do a DNS lookup and I cache that, that's state, right? And configuration changes. Right. Okay. So if all our stateless containers are really stateful in some way, then that kind of starts to answer why we might want stateful containers. And it's all the same reasons that we wanted stateless containers, right? We have immutability, right? We can deploy a versioned artifact. Well, except for the persistent data. We have minimal overhead. We can ship just the application, and except for the persistent data. And we have portability, right? Same thing in the laptop as you have in production, and except for the persistent data. Okay, so now we're getting down to what the problem is here, right? The challenges of state are actually the challenges of persistent data. Well, that hasn't really changed for containers, right? We had the same challenges of persistent data when we had VMs, right? Most of what people consider to be the challenges of persistence in containers are actually self-inflicted, right? I was talking a bit about a second ago about this kind of weird conflation of 12-factor with containers and with microservices, right? And so what we really have is this kind of overly opinionated, dare I say, religious view of what is supposed to be going on inside a container. And that is what's causing a lot of the challenges of the so-called challenges of running persistent applications in containers, right? So let's start with myth number one, which is that a container is your unit of deployment. Seems like it, Docker run, container. Right? But really, particularly we see now as the container orchestration frameworks have started to become more powerful, a group of containers is your unit of deployment, right? Your Kubernetes pod, your Swarm stack, your Triton deployment, which is coming in the next few months, Which means it's okay to have other containers that help you out here, right? So you have your application, but there's going to be some other containers around that, or maybe it's just processes. We'll touch that. All right, myth number 2, a container can contain only one process, right? I promise you, no one is going to take away your DevOps if you run an init in your container. I promise, it's okay. Like the people who write nasty comments in Hacker News are not in your data center, like looking at your applications. It's true. And in fact, a lot of applications have this cool new thing called fork. And if they do that, then they're going to be in real trouble if you don't have an init system that can actually clean up after them. Over at Joyent, we've been running multi-process containers. They're called zones for quite a long time now. And you can see those in Solaris zones and BSD jails, right? It's the same concept, right? It's a process and its process tree. It is not actually a VM. Right? Myth number 3, and this is really where we come back to the notion of stateful applications, that a container can't persist data. A stateful container can persist data so long as it has 2 things. It must participate in its own lifecycle, and it needs some help from the infrastructure. Did I say infra and then let that go? Oh, that's terrible. And in fact, a stateful container probably should persist its own data if you care about application performance, right? Or if you want to know if the application actually needs to be able to, if the application wants to know what the heck is going on, it actually should be persisting its own data. And what I mean by that is, so a lot of the solutions that we've seen that have come out of the container ecosystem are talking about like network attached storage for persistent applications. And if you have tried to run a database with network attached storage, then you know that you have an entire new murder mystery every time that you have a performance problem, right? In containers with the overlay file systems, if you just try to run it as a part of within your overlay file system, you'll find that the overhead of those overlay file systems, you lose a lot of IOPS to that, so that is also not what you want to do. All right, so given that baseline, what we're trying to do is we're trying to take like this developer experience, right, which is Docker run, awesome, to a production-ready environment for stateful applications. And a lot of folks are willing to sell you some kind of service or setup to that. Again, kind of going back to this notion of the 12 factor, there's this really weird thing in there, which is, and then there are backing services, right? And it's like, this kind of like vague, then there are some backing services. And the backing services is where all your data lives, right? So this is actually where all your business value is in these imaginary, this kind of like vague, hand-wavy backing service, right? So, because I kind of think that, a lot of the container ecosystem got focused around this idea of container orchestration with stateless services, and the reality is, who cares? Right? Stateless applications are the easiest freaking thing in the world to orchestrate. Like, that's so easy. Like, it's just not an interesting problem to solve. Which is why like there were 15 new container orchestration companies that were all trying to solve it for you. Okay. Now, again, most of these companies are building open source software, which is very cool. But I want to propose a different approach, and it's not about taking a specific piece of software, but an approach to building software. And the idea is what if your containers were self-aware and self-operating? And I want to change this a little bit, because earlier at an earlier talk from John Gossman from Microsoft, he was saying, in the next few years, we're going to stop talking about containers and start talking about applications again. And so let's actually prove him wrong and start talking about them today, right? Because a container is just a process. So what if we took a different approach and said, what if our applications were self-managing and self-operating, right? What does this look like? Okay, so every Hello World Docker, why is this important, right? So every Hello World Docker looks like this. Docker run, my app. Does anybody's production app look like this? No, right? Everybody's production app looks more like this, right? And this is a really simple application. There are two business process services here, customers and sales, and all the rest of this is the stuff that you need to really run these things in production, right? We have load balancing, right? How do we route between different instances of a service, or sometimes even how do we route between different functions for the same service, right? So read versus write concerns. We have replication and failover. We have data mirroring or replication and sharding, obviously very important for our stateful apps. We've got the notion of service discovery. How do our services find each other within our data center? How do we ship logs? How do we monitor for failure and performance? And how does that information feed back into the scheduling decisions that our application makes? So I want to dive in a couple of these problems in a little more detail. So let's start with service discovery. My app. Now, like many apps, my app has a database. So first question here is, how does this app find the database? Now, maybe we can just use DNS. But there might be some complications to that, right? So if my database is sharded or replicated, DNS doesn't know about those application level concerns. If I am doing a NoSQL database, this is like Cassandra or this is React or Couchbase or Volt, right? Any of the DynamoDBs, any of the Dynamo-based databases, the client knows what shard it's talking to, and so the client, the application, needs to know the real IP address of the thing it's talking to. Like, I can't just call this like cassandra.example.net and like it works. If I lose a node in that ring, even if that did work, if I lost a node in that ring, the client would need to know that I lost it. And many of our common application frameworks, unfortunately, permanently cache DNS for their upstreams, right? Anybody run Django or Rails and ever, and like it looks up the thing you make a query to the database, it looks it up once, and then if you change the C name that your database is pointed to, you have to restart all your app servers because that's the only way it runs. Just terrible, by the way, but okay. The problem of load balancing. So this is kind of a really stupidly simple microservices application. It's microservices because they talk to each other, I guess. That's like, nobody's been able to define for me what a microservice is, but okay. So we've got customers and sales and Nginx that does the routing from the outside world. And of course, we're web scale, so we scale out. We have this question of like, well, how do apps update their peers when they scale out, right? Like, so how does a customer's app know I just added 2 more sales nodes? Now, one option for this is what I like to call the load balancer culture, right? And this is if you're on Amazon and you're running everything in as EC2 nodes and you're talking to an ELB, this is what you do. If you're not on Amazon or you don't have everything as one application per VM, then you've got some kind of load balancer like HAProxy or Nginx, and we have to update the backends of Nginx. So, well, how do we do that? We've also added network path length, of course. We've added a single point of failure. Hopefully, it's HA at least. Alternately, although it looks very different, in terms of topology, these kind of service proxies that you're seeing in Kubernetes and some of the other things like Linkerd or Bamboo or Envoy is all basically the same thing. We just move the load balancer into the container or onto the VM that the container is sitting on. Same basic setup. Problems of automated failover, right? So everybody's favorite database, right? No, nobody ever says, yeah. MySQL with asynchronous replication, right? So we have the same notions of service discovery, right? So how does the client find the database? How does the replica find the primary? But we have these other more ongoing concerns about how does the primary tell a replica where to start replicating from? How do we orchestrate backups? How do we update, how do we promote a replica or update the clients when we do a failover, right? So these are application level concerns that can't be solved with like a TCP proxy, right? Persistent data. And this brings me to myth number 4 about containers, which is that host volumes solve the persistence problem, right? So like we just -v mount my volume wherever and everything's solved. Except that we haven't solved anything, right? Because that blob of data is just now on the VM that you're running instead of inside the container. Like, congrats, like the data's still like on the it hasn't moved, right? It's like we still have the problem of like, well, what if the VM goes away? What do we do with that data? And by doing that, we actually make it harder for the application to participate in its own lifecycle because we've given it at one level removed from the application. So the problem that we're really trying to solve here is data gravity, which is a ridiculous term, but right, which is this notion of like, I have a bunch of data, a bunch of like blobs on disk that I need to figure out what to do with. All right, so let's talk, so these are the problems. So let's start to talk about what are some of the incomplete solutions. I'm not going to call these non-working solutions because they've obviously worked for many of us for many years. Let's start configuration management, traditional configuration management. Calling configuration management these tools traditional is ridiculous, but you know, everything moves so fast now, right? Okay, so in the configuration management world, we've kind of broken the model that we have that Docker gave us, right? We generally are not going to be running a CM server in our local development environment. Most of these tools don't have any way of doing a service discovery on change. And the agents are very heavy, right? We wanted to ship just the application, right? And so if I'm shipping a little Go binary or I'm shipping, you know, a giant Java application, I don't want to also ship the Ruby runtime with a C compiler because you can't ship anything in Ruby or Node or Python without a C compiler attached to it too, right? So like that's not what I want to do here. The as a service stuff, right? So database as a service, DB as a service, right? So a lot of vendor lock-in on that. It can be very expensive. And that's, you know, it's TCO cost. It doesn't involve some of the, you know, obviously there's a lot of opportunity costs that you're offloading onto them that, you know, that's a legitimate choice to make in some cases. These things are very hard because generally though you don't have access to, you know, get on the box that it's in. These things can be very hard to observe and debug. I once had a multi-day outage with RDS because of like IOPS stuff, and there was just no way for me to find out what was going on disk there because I didn't have root on the box. So making things hard to observe and debug means that you have performance and reliability problems. The platform as a service, same set of problems, right? So this is Google App Engine, Heroku, Beanstalk, I think is that logo. Scott Hanselman this morning was talking about, you know, taking advantage of modern abstractions and being aware that they are abstractions, but also that we need to know what's going on under the hood when things go wrong. So I'm not saying never use a PaaS, right? Clearly that would be a silly thing for me to say, but I am saying you need to know what you're giving up when you choose to use a PaaS, right? If you choose a platform where ultimately someday your engineering team is going to have to say, our only solution to this is to call support, you've made a certain choice about what your trade-offs are, right? And maybe that's the right choice for your team. The mega orchestrator. So this is Kubernetes, you know, Mesos, et cetera, right? So Kubernetes was missing a story about stateful applications from the very beginning, right? So if you go back to the original like pet set GitHub issue, it's really funny because they're like, yeah, well, we're not going to handle stateful applications for a long time. It'll be like a year, and then pet set was in beta until like this summer, and then they renamed it stateful set. And it essentially says that like, well, part of the understanding of how the application behavior is going to be in Kubernetes, and part of it is going to be in your application, right? Because you have these modules that are specific to the kinds of distributed stateful applications that you're running. But that creates a tight coupling between the orchestrator and the application, but it also splits the understanding of the behavior so that the application developer doesn't have a full understanding of what they're doing. Oftentimes, these orchestrators are very heavyweight, although now we have things like Minikube, which apparently is okay. I haven't used it myself yet. But generally, that means that the developers are not running the orchestrator in their local development environments. And we all know what that means, right? So we've shifted responsibility for the application behavior away from the application developer and into this orchestration framework, and that disempowers our application development teams, right? We want it to orchestrate on my machine too. Okay, so back to this question here of what if your containers were self-aware and self-operating? If your applications were self-aware, self-operating? We want to solve these problems of service discovery, load balancing, data management, persistent data, but in a portable, scalable way that empowers the application developers, right? Because the whole reason that we chose things like Docker and containers was to empower our application developers and to improve their velocity, right? So, I'm doing good on time here. All right, so at Joint, we've developed a design pattern called the Autopilot Pattern. It's a design pattern for self-managed and self-operated applications. It is not a piece of software. And I'm actually going to show a couple different ways of doing this with different pieces of software. The idea is that application containers can autonomously adapt to their environment and coordinate their actions through some kind of globally shared state. In a lot of these, we'll use console. This design pattern has been used at both startups and major retailers. And again, it's not a piece of software, it's a pattern. So we're going to make applications share responsibility with the environment, with the orchestration layer for their own lifecycle, right? Startup, shutdown, scaling, discovery, recovery, telemetry. And again, it doesn't have to be containers, right? We're saying applications. And the goal is to empower our development teams to operationalize their applications. We want the production behavior of our application to be fully understandable by the application developer. Okay, very short demo of what this looks like, kind of on the super quickie version. Okay, is that, yes, okay. So this is a hello world application. We're just gonna go Docker compose, D, right, and I'm starting, this is that microservices where I had hello, it was customers and sales, and this one's called hello world for some reason. Right, so I've got a couple of servers here. I'm gonna go, oops, Docker exec. Right, so I'm looking at the Nginx configuration that's there, and I see none right now. Give it a second here. Right, and so now I've got one instance of hello and one instance of world. And we saw a second ago, I had no instances of either of them, right? So these applications came up, coordinated their state, and Nginx rewrote its own, the Nginx container had its configuration rewritten by itself and was ready to serve. So we're gonna go, let me actually really quick, this way, yep. It's going to not work on me right now for like the first time ever. Come on. My console instance must be running. Sorry. Well, that's alarming. I think my Docker engine just crashed. I'm running this, this is local, right? I'm running this locally against Docker, right? And it's just, oh, there we go. Okay, so I've got my instances. Let me see if I can get this up now. I'm having something goofy with my networking here. All right, so we'll come back to that. But what I'm going to do here is I'm going to go Docker compose, scale, hello, 3, world, 2. And then, so I don't have a giant mega orchestrator here. Right? I'm just using compose, which is pretty much the dumbest scheduler you could ever do, right? It can't even like re-provision things. Right, so I started these up, and if I look, I should have a bunch more. And if we go back to our exec, we should have, within a couple seconds here, okay, right? So I now have new instances of the servers that popped up in my Nginx configuration, right? So now I'm doing all my routing that way. Okay, I don't know why that other thing isn't working. We'll come back to you. All right. Okay. So that's a super simple example, right? And we're going to have a much more complex one in a minute. To do this, though, we have 3 requirements from our infrastructure. We need some way to be able to provision containers across multiple compute, right? Some kind of compute substrate. I was using compose on that example against my local Docker engine. That works fine. But I need some kind of cluster management and provisioning. So I need a way to get my containers onto the VMs or the physical hardware that they're running on. It seems obvious. Lots of options for that, right? Triton, of course. I'll tell you that that's the best one to use. Docker Swarm, Kubernetes, DCOS, Cisco's Mantle project is actually pretty cool. We need network virtualization. The core example of this is VXLan. And the idea here is that we want the IP inside the container, meaning the IP as seen by the application, to be the same as the IP that other applications will use to reach it. Let's look at why. So here's our data center. All our VMs are 10, right? And if I look into one of these, right, and so, okay, so this is a physical instance. This is one physical instance or hardware virtual machine, so KVM, Zen, whatever, your AWS thing. And I've got a customer's application in a container, and it needs to talk to sales, and it's going to advertise where it is to a service discovery, and this is HashiCorp's console, which is my favorite tool for that. But you could use Zookeeper or etcd. There's a couple others, but those are the good ones. So in the out-of-the-box Docker Bridge networking, you have NAT, right? So it creates a virtual IP address for your application, right? So 172.17.0.2, and it's going to use this NAT interface to talk to the outside world, right? So the 192.168 is the routable IP address on the LAN. So when it right, so our source IP will be, our source IP to when we talk to sales will be 192.168.1.100. And yes, I realize this is NatPat. If you're really pedantic about it, like go somewhere else. Okay. But when our customer's application wants to tell sales where to find it, it's going to talk to console and say, hey, this is my IP address because that's the only one it knows about. And so when sales asks console where to find it, it's going to get, well, 172.17.0.2, which of course there's no route to that host. You can't, that doesn't work with NAT. We can't take advantage of, unless we create a persistent connection between customers and sales that's initiated by customers, that doesn't work. And because we're probably going to be reaching sales under the same mechanism, like it really doesn't work. So we can't do that. Another model is Docker host networking. So in this we say, well, we're not gonna have the virtual interfaces, right? We're gonna give each of the containers access to the host's network stack. So when I talk to this sales node, I'm using the IP address of my LAN interface. And when I register with console, the source IP address will still be 192.168.1.100, so that'll work. And when sales tries to reach it, that'll work fine. Okay? And this worked, right? But the problem is when I have two of this container, right? And they both want the same port. Now I have port conflicts, and that's no good. Now, that being said, this is totally okay if your application can coordinate with the scheduler to do port assignment, right? Like if your application just takes like an environment variable or something like that your scheduler can set for it as the port that it's listening on, like this works fine. And in fact, the performance is awesome because you're just using the host stuff, the host interfaces. It is not safe for multi-tenant environments. So they actually share the networking space, so that's not okay for some kind of environments. Now, if you own all the containers that are in there and the host, awesome. We at Joyent, we run multi-tenant containers, so like we can't do that. We run customer containers, right? We can't do that. So VXLan and other forms of overlay networking do this, right? Each container gets its own virtual IP address, and that virtual IP address is addressable on the network. So this customer gets 192.168.1.100, and this one gets 192.168.1.102, and that works just fine. There are some options for that. Triton, of course. Cisco's Mantle project does that. DCOS, Docker Swarm. Kubernetes kind of has a different model than this. It effectively gives you the same thing. There's a project called Calico, which is very interesting. Again, a different model, but effectively gets you the same thing using BGP. On Triton, this is a little tiny pitch. Each container gets a virtual NIC. So you have a layer 2 private VLAN for all your containers, and you can set up firewall rules and whatever there. And then you can optionally get like a publicly routable IPv4 address. And each platform is going to implement this differently from each other, right? So like, but the important part is that the IP address that you see in the container is the IP that other containers within your application will use to reach it. The third piece we need is some kind of infrastructure-backed discovery bootstrap. This is a little, so I was talking a little bit about, well, DNS is not all that awesome, but you need it a little bit. And here's why, right? So our microservices application is going to use console to coordinate services. Well, how do they know where to get console, right? So like you need some way of bootstrapping this problem, right? So one of the ways to do that is with some kind of infrastructure-backed DNS, where you have fixed instances within your application that know that can be provided to the containers through your scheduler. On Triton, we have something called container name service, which effectively ends up being the same thing. You can run console on each node, Zookeeper, etc. All right, so with those three things, what we've said is that those are our requirements to make applications share responsibility for Startup, shutdown, telemetry, recovery, discovery, scaling, right? So, but you might already be saying to yourself, well, that sounds awfully complicated, right? Like giving my applications these kind of responsibilities is a bit of a pain. And I'm going to tell you it's not complicated, but it is complex, right? Complexity is conserved within the system, right? This is information theory, right? But so what we're talking about is what abstractions are we choosing, right? If you use, and whether you understand those abstractions. Somebody owns this complexity. Now, whether it's your team or whether it's some other team or whether it's a third party is up to you. You get to pick where you want this complexity to live. Now, if you're Google, you write all your own shared libraries and everybody's happy. And in fact, you fork everything that you, from the open source world you use, and awesome. If you're an enterprise with some kind of like service-oriented architecture and everything you've written is on the JVM, you may use Scala and what's the Clojure and Java, but you're gonna have some shared libraries within your organization that does like your RPC framework, let's say, right? And maybe that's a great option for you. If you're a smaller org, if you're a polyglot org and your CTO is one of these people who's like, we use the right tool for the job all the time, and so you have like 5 teams that use 5 different languages, like you're gonna write them all in C. You're gonna write all this, your RPC framework in C, right? No, you're not. You're gonna like not have an RPC framework and you're gonna suck. So like that's not gonna be an option for you, and you're going to need some other way of handling this. And this is what the kind of the rest of the talk is about. So we might need some help, and let's look at I want to look at 3 kind of broad strokes implementations of what this is. So the first is Kubernetes with some Bash. When I was doing the talk, doing this talk, I was like, oh, I need a logo for Bash, and I was like, does Bash even have a logo? That's Bash's logo. I didn't even know that it was such a thing. Okay. So here's our Kubernetes pod, right? So this we've got customer. So this is in our compute node. This could be a VM, doesn't matter. Our customers container, our console agent, which is either running in the VM, maybe it's running as a sidecar container, and some kind of like setup container, which is definitely a sidecar container. So our console agent will coordinate with the console discovery service, and the setup container will get some data out of that, and it's going to write some information into the customer's application, and the customer's application will use that to reach the sales application. A couple of caveats with that, and this works. This is like a totally workable option. This is how, if you're running Kubernetes, this is how you're doing it. If you have any kind of like non-trivial application. This setup container, because it's reaching into the other container, needs some level of elevated privileges. Now, hopefully it doesn't need the Docker sock, because that means that setup container is root in your infrastructure. But it maybe it's writing into a volume. Maybe if you've really done your homework, it's just making an API call, which is awesome, and that's a great way to do it. If you're in an organization where the application development team and the platform team are different teams, particularly if they're at constant war with each other or something like that, this model might be problematic, because if you need, let's say you do need the Docker sock, like they're not giving it to you because then you're root on the box. So that works in some orgs, in some orgs it won't. This setup also, the local development story for this needs a little work, because we've got a Kubernetes pod, right? And maybe if we're not using Minikube, that's a bit of a pain. Minikube itself is a bit of a pain. There's another application, this is very cool, called Habitat. This is from Chef. Habitat runs a little supervisor inside each of your containers. It's PID1 within the container. And it doesn't have to be, this is actually agnostic to containers. It's actually pretty cool. So it runs a little supervisor, runs PID1, and that PID1 coordinates with all the other supervisors within your infrastructure. They gossip configuration changes to each other. And they trigger lifecycle events. So we could set up, so this thing could say, oh, when something changes, do this setup command. Which is pretty cool, because we just created a Kubernetes pod all within a single container. Think about it, right? We've got our service discovery data going around. We've got our lifecycle hooks, and we've got our application. Except now it all lives in one container. So it's agnostic to the container runtime entirely, right? We could even not use containers if we want, but we don't need Kubernetes here to do this for us, or whatever it is. This model is really cool because you're writing your own lifecycle hooks. You don't need a separate discovery server. That's both cool and not cool, depending on what your needs from that discovery server are. This is not a CP system, it's a gossip system, so It's an AP system. If people know their CP versus AP, their FLP. What is that? FLP result? Am I getting that right? Anyway, but basically that means that like configuration information is eventually consistent. It's not immediately. There's no consensus around it. They have some ways of like building consensus on top of it, but it requires a little work from you. And there's no ties to the underlying host again, so you can pretty much run this thing on your dev, on your laptop, without your container runtime, which is really cool. I really like this tool. This is awesome. The solution that I wrote at Joyent is called Container Pilot. And it, much like Habitat, is an init system for running distributed applications in containers. It manages lifecycle events, health checking, and watches the discovery catalog for changes. It updates the configuration on upstream changes and provides some performance metrics. So this is kind of what an application stack looks like when you're running with Container Pilot. So we've got our app, we've got Container Pilot running as PID1 in the thing, a console agent inside the container, and a setup thing, right? So, hey, that's a pod. And you'll note this is very similar to Habitat, which is like both projects were started right around the same time, independently and quietly, and like we both found out about each other about 6 months ago, and that was kind of cool because I got to meet the CTO of Chef, and we were like, oh, that's so cool that you did this and we did this, and then anyway. This is a little bit one of the things that's a little bit different here is that because we're relying on an external discovery service, we're using its abstractions rather than implementing a gossip protocol ourselves, which is good because we just have a smaller team. Like it was mostly just me at first. We have some community contributors now. Console is also a CP system, so we can do things like locks and get sessions and things like that within console. So that might be more convenient for you if you're doing that. For the rest of this talk, we'll be assuming that we're doing this. So this is what this is our Container Pilot pod, right? Or Autopilot Pattern pod. So let's get rid of the VM for a sec because we don't need that for the rest of our discussion here. So the console agent is going to discover service discovery information and configuration data with the console servers. Container Pilot is going to be acting as PID1 within the container. It's going to register services as they become alive, as they pass health checks, and it's going to fire lifecycle events and watch console for changes. Again, it's agnostic to the container runtime. One of the largest contributors of this is running not on Joyent at all. They're running on Mesos on Azure, and they were recently acquired by the Fortune 1 company. We won't name them. The application developer writes the lifecycle hooks, and this consensus is in the discovery server. Version 3 of Container Pilot is coming out in the next month or two, depending on how fast I can get it done, which is going to have some new hooks for monitoring, configuration updates, and some optional hooks for a Triton scheduler. If once that becomes alive, we'll be ready to use it, but that's optional. Like you don't need to use it if you don't. It doesn't have to be on Triton, is what my point is. So let's look at that microservices stack again. How am I doing on time here? Not good. Okay, we're going to go through a little faster. Okay, so that same application we were looking at earlier that I did the demo on, this is what it looks like. So Container Pilot is running as PID1 in the container. It starts a console agent when it starts up. That console agent gossips with servers. It runs a setup first, which says, hey, get some configuration data at a console and write that into some kind of config file. And then once that setup task is done, that process ends. It gets reaped properly because we know how to write an init system. And we launch our application and we register that with console. If one of our sales nodes here dies, it's going to, that information will be received in console. And we'll talk a little bit later about how that happens. The console server will make sure that all the console agents know that. That will fire some kind of event handler, which is, the application developer decides, hey, what do we do about that? In this case, we're going to rewrite the configuration and do something to do our application, perhaps. Maybe we SIG-hup it if it handles that gracefully, right? In the case of Nginx, you can pass SIG-hup to Nginx and it'll gracefully reload that configuration. The important point here is that the events are provided by Container Pilot. The behaviors are defined by the user. And by user, we mean application developer, right? So the entire behavior of the application is owned by the application development team. Here are the events that we provide. So startup, shutdown, something changed, a service is healthy, a service is unhealthy, something stopping, one of the tasks within the container exited, either good or bad. And so this is the application we demoed a minute ago, right? So we've got nginx, hello world. And this is kind of what it's, so like in our Docker file for nginx just looks like this. So this is pretty much a basic nginx Docker file, except that we're installing Container Pilot into it. If you look at this repo, you'll see that we like always check the checksums, please. Don't just like drop binaries in your containers. We also have given it some tools. We're using console template to rewrite the config and a little bash script in there. And then our Container Pilot configuration just looks like this. This is version 3 syntax, which isn't, you know, this is available if you wanna try out like super alpha software. But this is what it'll look like when it goes live. So we have a list of jobs. So the job, and this is like, you know, jobs like an upstart, you know, or I'm not going to say the systemd word, but one of our other supervisors, right? This is, you know, we define a list of jobs and that's what we do. So the first job there is the pre-start, which says we're going to exec this pre-start application. The next one we have here is nginx, and we see that we're execing nginx when the pre-start event exits success, right? Kind of reads like English a little bit. We also see how to health check it. It's just going to run curl locally. We have 2 more jobs here, right? So we have an on change for hello and world, and those we're going to run when watch.hello changes and watch.world changes. And what are those watches? Well, they're this. So we are watching console for these 2 applications, right? So watch hello, when that changes, that on change handler will run, and when watch world changes, that on change handler will run. All right. Okay. So we said this is a talk about stateful applications, right? Okay. So everybody's favorite database again. So MySQL replication. Let's actually get this started. Just sets up my environment here. All right, so we're going to go. All right, so first things first, I am pointed at our Triton data center. So I'm using the Docker API, but I'm launching containers across the entire data center, which is kind of cool. And we're going to go. And again, I'm just using Docker Compose as my dumb scheduler here, so I'm going to start that. That is going to take a second to come up, so we're going to come back to this. So before I dive into this application a little bit, this is MySQL. It's doing asynchronous replication. Asynchronous replication will not give you the guarantees that you may want. And that's just inherent to asynchronous replication, right? So when we do failover, we are going to be unavailable for writes. We can get stale reads during failover. We can drop client acknowledged writes during failover. But that's how MySQL works. If you don't want that, don't use MySQL. Use something with synchronous replication, please. Okay. Just wanted to get that out there. Okay. So async replication is not CP in the CP versus AP sense, right? We might be able to get it to be AP. We're actually not going to be even fully AP for writes. We will be AP for reads during the entire setup, though. Okay. So this is our entire stack. We've got, you know, this is all open source. What I've got here is a Python application that we got in here, which is doing our event hooks, the Container Pilot configuration, MySQL configuration, and a Docker file and some Compose files. We're just using Compose to launch this. This is kind of a dumb, simple example, which just shows you how little of a scheduler you need. Basically, you need something to launch it onto the host, and after that, it handles everything else. So this is what our Container Pilot configuration looks like for that. We've got a pre-start, which is again just running this Python application. Ordinarily, I don't like to ship like big runtimes with an application, but the MySQL container already has a lot of its tools, or a lot of the MySQL tools are written in Python. So writing this application in Python was a good fit because I've already got Python runtime going with shipping with this. My application that I'm going to run is MySQLD, of course, and it's going to, when the pre-start exits with success, we will run MySQLD. Here's how we'll health check it. You note that all these behaviors live in this managed PY application. I have a snapshot check. So every 5 minutes, I'm going to check whether it's time to run a snapshot, which is defined by my application code. I'm going to give it a timeout of 30 minutes. It'll fail if that doesn't happen. We're not going to really get, but this is how I can do backups, right? And what that snapshot check is, in this case, is we're just using Percona extra backup, right? So we get an atomic backup of one of our replicas. And then for watches, we're going to watch for a MySQL primary service. And when that changes, we're going to run this onChange handler. All right, so let's look at our MySQL container. So we've got container, console. Container pilot is PID1 in the container. Oh boy, I'm running late. Okay, it's going to fire up console agent. It does gossip. And then its behaviors will all live in this managed PY. And then it's going to launch MySQLD and whatever its configuration is. Of course, in our stack here, we'll have some other nodes. And we are going to have an object storage, which we're going to use for our backups, right? So this is our snapshots. This could be S3 if you're on Amazon. If you want to be really cool, you can do it on Triton Object Store or Manta, which is ours. All right, so this is what it's going to look like when it's all running, right? We've got all these components. So let's walk through what it looks like during initialization. And this is that pre-start application. So that managed PY runs. It's going to say to console, has a snapshot been written to Manta? So like when the application starts up, it doesn't know that it's our first node. So console might say to it, no one has written a snapshot to Manta. You must be the first one. So, oh, well, then I must be the primary. I'm going to initialize the database, which means I'm going to write some configuration. Alternately, if this is one of our later nodes, which will come up later, it's going to say, yes, I have written a snapshot, and this is where I wrote it to. So then our application is our managed PY application is going to say, okay, I'm not the first MySQL. Let's restore that snapshot, so get it from the object storage. All right, so let's, we should probably be up by now. Yes, cool. All right, so what we're going to do here is we should see our application container. And we're going to look in here at some of its logs. And I'm cheating by knowing where I need to go. Right, so I'm looking for a particular line in its logs, which is this inno backups, right? So inno backup X. So this is a Percona backup tool. So what I'm doing is during the pre-start, if I'm the primary, I took a atomic snapshot of where I was. So I did my initial setup, like I set up who my initial users and initial schema, and then I snapshotted immediately. And then that snapshot is getting uploaded to my Manta object store, my S3 equivalent, right? So where other instances will be able to get it. It's also written, I don't have it, it's not in the logs here, but it has also written a key in the console so that new instances that come up will see that. All right, so if so this Triton IP MySQL console is just getting the IP address of my console server, right? So I am asking it for a service named MySQL primary, and I have one instance up as MySQL primary. Of course, I do not have any replicas, right? No replicas because we didn't start that yet. Okay, and I think I wanted to do sorry, real quick. I have a note here. Oh, okay. Well, I shot it a little bit ahead. Okay, so service health. So what we've got here is that on each health check, our application is going to say, our managed PY application is going to say, who is the primary? And console, which has a key that says who the primary is, will say, well, maybe you are, right? In which case, if our application agrees with the data that I have locally, it'll confirm that and it'll say, okay, here, have a heartbeat. And registry maybe is the primary if you don't already, by the way. which is, so there is a lock in console for who is the primary, and then there is the service registration of the primary, which that diagram is maybe not all that great. Another possibility is, of course, that somebody else is the primary, in which case, if we have that information, we're going to say, okay, confirmed, have a heartbeat. The heartbeat that we send to console has a TTL on it. If that expires, then this node is marked as critical, and it may result in a failover, and we'll show that in a sec. Right? So another option here is that we might say, who's the primary? I don't know. So in that case, we're going to have a little problem. So let's do a little bit further here. Let's go up to, all right, so I need some more instances to show this, so we're going to scale that up. And while we're waiting for those to come up, we're going to come here. And we're going to talk about primary election. So we're relying on console's raft for consensus, right? So what in that case, if we get an answer that I don't know who the primary is, every instance of that managed PY application will say, I'm the primary, and give me a lock. So only one of them will win the lock, right? This is a CP system, so that lock is guaranteed to be atomic. So if I fail to get that lock, console will tell the application, well, no, you're not the primary, sorry, like go start over and try to figure out who the primary is. Because this is pretty simple, we just start over at like, who's the primary? And then we ask again, right? If it is the primary, then it'll say, okay. And at that point, we'll take our configuration. So this is our configuration that said, the service that we're advertising to console is MySQL. And we're going to rewrite the configuration and reload it. And so that means that now our managed PY application that means that Container Pilot will be advertising this node as MySQL primary to console. And so that means that only one instance of the application will be running as MySQL primary at a time. So let's check on our replicas here. Okay, we've started. So if we go Docker PS, we see 3 instances now. This is a little, one of our APIs that says, tell me what the compute node, the physical compute node that this is on. So I've used my Docker client, I'm pointing at the entire data center, so I'm going to do this. And that Docker Compose is marked with an anti-affinity, so none of these nodes should land on the same physical hardware, right? Because that would be stupid. So we've done that. All right, so now what we're going to do here is if we check one of our instances, we should see, this is one of our replicas, MySQL 2. We see that we've got a copy back here of that InnoBackupX, right? So it has snagged the snapshot from our object store and has used that to restore itself. So now all my schemas are the same. And if I ask console for replicas, I should see oops, what the heck happened there? Weird. All right, so I see 2. All right, so I have 2 nodes here. All right. So now we're gonna get crazy because it's all cute to say, like you say, oh well, you've got a replica there, right? But what we're gonna do instead is, well, first let's make sure we've got. So we cheated a little bit here, and in our setup we have a schema already set up, right? So this is a really simple ID name with an auto increment, and let's do an insert. Right, so I'm actually just, this is not like usually you'd have a client application. I'm just reaching into the container and doing, running my SQL client in it with my super secret password, right? All right, so I'm inserting a value into that table. Okay, and if I now I'm going to ask MySQL 3. Okay, cool, right? So that replicated, which means I actually have replication among all my nodes. All right, so last item, we're running close to the end of time here. So failover, right? So this is what this is the really hard one, right? This is the tricky bit. So earlier I was talking about what happens if the health check fails, right? So the health check, in addition to doing all the work about like figuring out the consensus, also just does like a select one on the database. It can, again, this hook, because it's user defined, can be arbitrarily enriched, right? Like, so we can check whatever we want. We could check if it was in a degraded state and say, well, you know what? Disk is really degraded or full. We're just going to say we're not healthy anymore. So in that case, the exit code of the health check will be not 0, because in Unix 0 is good. And our TTL will expire, right? So at that point, for our other instances, right, so now we're in the replica, console will tell container pilot, because container pilot is watching those keys, the primary is gone, I don't know where it is. So then, all the managed PY instances will say, okay, I'm going to attempt to handle the failover. Now, you might be asking, why aren't they saying I'm the primary, right? Why aren't we just doing it that way? Turns out, like, if you try that, then it's really easy to get, which was, I'm going to admit, was version 1 of this. It's really easy to get data corruption by having your replicas in different, at different replication points, because you can have one that like has writes that are not going to appear in the primary anymore. So instead, what we're using is an Oracle tool called MySQL REPL Admin, and what it does is exactly what you should be doing in this case, which is it's going to run around all the instances, say stop replicating. Figure out who has the highest transaction ID, make sure that all the transactions appear in all the instances, and then say, you're the master now, primary, right? So once that is done, we'll say, who's the primary now, and console will have that answer. And we'll change master to whatever, right? So let's just finish up our demo real quick. Okay, so I just stopped my primary. I'm pausing for dramatic effect because it's going to take a couple seconds to kick in. Okay, so what we should see here is if I go, I'm just going to grab from one of the logs. Now, I don't know which of the instances is going to be the primary when this is done, right? It could be 2, it could be 3. I don't know. That's kind of the point. I, as the operator, don't care which one because they're all identical. It should be able to figure it out for itself. Right, so I should see here one of these is going to have executed the failover. Cool, and we got lucky that this is the one. So what we're seeing here is our managed PY application said, this instance got the lock. It's executing failover with these 2 candidates, meaning the only 2 candidates we have. It does this whole thing here where it stops the replication and figures out which one is going to be the new master. And then we get a replication topology health at the end, where one of them is the primary and the other one is the replica. Right? So now, if I look for the replicas in console, I have 1 replica. And if I look for the primary, I have 1 primary. Of course, the proof is in the pudding. Let's write to the primary. Okay, we've written to the primary. And if I bring up that same query we ran before on number 3, I've written that row to both machines now. So the replication has failed over correctly. Okay, that almost always works. This application is still in beta. It's still kind of, we can work through. Okay, so this was an example of a design pattern. Notice that like you could totally have built this yourself without Container Pilot. You could have built it on top of Habitat. You could have built it on top of Kubernetes pods. It doesn't matter. But the point is that we're making applications share responsibility for these behaviors. And that allows us as application developers, as the people who own that application, the team who owns MySQL within your organization, now has the power to understand what is going to happen in their application. It doesn't matter which tool you use to get there. The goal is to empower the development team to operationalize their application. Everything that I've done here today is open source. Try it, report issues, contribute. Thank you very much. I think we are at 5. So unless somebody is very quick with a question, I think that's going to be it. I hit it right on the nose. I didn't want to answer any questions. No. Thanks, folks.